Well, I just wanted to do a quick video on 2.7 and related rates. Maybe we'll do 2 or 3 examples. So I'm going to do the example in the book. This is on page 291. And I'm going to try this one on related rates. Actually, it's on 290 at the bottom. And it says a restaurant supplier serves the restaurants in a circular area in such a way that the radius is increasing at 2 miles per year. At the moment when the radius equals 5 miles, at that moment, how fast is the area increasing? So let's take a look at this picture. This guy started out kind of with a circular route. And this distance from here to here, of course, is the radius. But as business got better, he started to expand his business out a little bit further. So we can see the radius is changing, but also the area is increasing. And we want to know how fast is this area increasing in comparison to how fast the radius is increasing. So when we're going to show an increase in the radius, we're going to write that as the change in the radius as compared to time, dr over dt. That would be the change. That's how fast the radius is growing. And how fast the area is growing is dA over dt. That's how fast the area is growing, and that's what we're trying to find out. How fast is this area increasing? Just because he increased the radius by a couple of blocks this way, how big an area is he getting now? So we want to know what happens when he finally gets out to 5 miles. This increase, maybe he's increasing a mile, and then all of a sudden he gets up to 5 miles. His rate of increase is 2 miles per year. So how do we do this? Well, first we start out with the basic formula for a circle, the area of a circle, because we're concerned with the area. So area equals what? Pi r squared. Okay, so now we're going to take the derivative of this using implicit differentiation. So this would be dA, but we're not going to put it in terms of x, we're going to put it in terms of time. dA over dt equals what? 2 times pi r, but we took the derivative of r, so it's dr over dt, right? So now we've taken the first derivative using implicit differentiation. This is what we're trying to find, dA over dt. And what do we know? Well, we know 2, we know pi, we know the radius is going to get up to 5. We want to know what and at that point, the rate at which it's growing is 2 miles per, it's going to grow up to 2 miles. Let's put miles in here. And it's finally going to happen when this is increasing at 2 miles per year. So if we multiply all this together, I had this multiplied out, and I can't find it. I guess I did it in the book. So anyhow, this would be 10 times 2, that would be 20 pi. That would be 20 pi miles square miles per year. Well, 20 times pi, let's see, use our calculator here, clear it out, turn it on, clear it. 20, see if I can put it up here where you can see it. 20 times pi, get it? 20 times pi, come on, it's not that hard, equals about 63. So this is the rate, dA rate, at which the area is increasing is about 63 miles square per year. So it sounds like a real hard problem, but basically it is if you don't write down what these things stand for. 5 miles is your radius, your new radius. That's how it's increased. And dr over dt is the rate at which it's increasing. And what we're trying to find is the rate at which the area is increasing. So they're not increasing at the same rate because this is getting much larger, significantly larger right away. So I'm going to try another one here and try to straighten this out at the same time. Okay, let me draw a line here. And I actually have a problem here. This is off, this one's going to be very similar to what we just did. So this maybe help you. I'm going to bring this down so you can kind of see it a little bit better. This is off an AP calculus test a while back. So it says a tanker is spilling oil in the Gulf of Mexico in an oil slick that is close to circular shape. At the time the slick's radius is growing at 5 feet per minute, the diameter is 800 feet. At what rate is the area of the oil spreading? Well, it may sound different from the other one, but it's basically the same problem. We have a circle here. We have a radius. So we usually start out by drawing a diagram if possible. And the rate is increasing. We have a rate, and we want to know when this hits 5 feet. We know the rate at which it's increasing. This is R. The rate at which that's increasing, dr over dt, I like to use a capital R myself, is equal to this isn't 5, this is just a rate. Okay, we'll get that. The radius is increasing at a rate of, here's the 5 feet per minute. It's increasing very rapidly. Okay, now we're trying to find out what is the rate? I mean, what is the radius? And the radius is 800 feet, but that's the diameter, so the radius is half of that. So the radius here is 400. And now we want to know how fast is this whole area increasing? dA over dt. That's what we're trying to figure out. So it's very similar to the last problem we did. Sounds like it's different, but it's the same thing. Area equals pi r squared, right? Taking this in relationship to time, dA over dt equals 2 pi r dr over dt. Just a matter of substituting in the values we have. Our values are going to be 400 for the radius. So let's write this down again. This will be 2 times pi times 400. And the rate at which it's increasing is 5 feet per second, per minute. So this was the number of feet, and this was feet per minute. So let's multiply all that out. Let's see, I think I already did. That's 10 times 4, 4,000 pi. Feet squared per minute. And then I calculated with pi, and it came out to be 12,566 square feet per minute that this oil slick is increasing. Okay, next problem sounds a little hard. We got a 13-foot ladder and it's leaning against a house. When its base, the base starts to slide out, and the ladder is starting to come down. By the time the base is 12 feet from the house, the base is moving at 5 feet per second. how fast is the top of the ladder sliding down the wall at that moment? So let's draw a little picture here. Okay, and here's our ladder, and it's against the house. Let's draw this a little taller. And it's right here. Okay, how long is this ladder? This ladder is 13 foot. Let me erase this a little bit. This is 13 feet. Let me move this down a little bit so you can see it better. Okay, now what's happened is the ladder started moving out this way. And it's moving at a rate of 5 feet per second. Let's call this X and this Y. So the rate here is dx over dt. That rate is 5 feet per second. It's moving pretty rapidly. And as a result, let's see if I can sketch this in. Let's try this with a different color of pen or something. Let's see if I got something here. Now how this is going to go. When the ladder comes down like this, we want to know how fast it's coming down. So we want to know the rate at which this is coming down, because that rate is not going to be the same as this rate. And when this X reaches 12 feet, right here, we want to know what the rate is that this is falling at. When it reaches 12 feet, it's going at 5 feet per second this way. But how fast is it coming down this way? Yeah, pretty scary, huh? How fast is this happening right here? So that's what we're trying to find. So one thing we might want to do is figure out how high off the ground it is at this 12 seconds. So let's take a look. This ladder is still 13 foot long. It hasn't changed. So this is still 13 foot, and this is still 12 feet. Now, how far is the ladder off the ground from here to here? That might be useful in calculating this problem. So x squared plus y squared equals with the height squared, the length of the ladder, whatever you want to call it. We call it the length. I guess you could call it C. You could call it C. H for hypotenuse. Okay, so X would be what? 12. And Y is what we're trying to figure out. And we know H is 13. So 144 plus Y squared equals 169. And we take the 144 to the other side. So Y squared equals 25. We take the square root. Y is 5. So this distance right here now we know is 5. So now we're going to try to solve for dy dx. So x squared, we're going to start out with the same formula. H squared equals h squared. X squared plus y squared equals h squared. Sorry, getting ahead of myself. Okay, and we know the height is, the length of this ladder is 13. So x squared plus y squared equals 13 squared. But that's impervious because when we take the first derivative, 2x dx, and we're doing this in terms of time, plus 2y dy dt equals the derivative of 13 squared, which is 169. What's the derivative of 169? It's 0. So it didn't matter what the length of this ladder was, really. Okay, So now we're going to calculate this out. We're going to just put in some numbers in here. We could rewrite this and do all fancy stuff, but I'm just going to put in my numbers. 2 is part of the formula. X, we know is it's going to reach a distance of 12. We know it's falling down at 5 feet per second. That's the way we want to label these. Plus 2, we know y is now 5, but we don't know dy over dt. And we know this is 0. So this is 5 times 12 is 60 times 2 is 120. Running out of room here. 10 dy over dt. I bring this over to the other side of this negative 120, and that makes sense because the ladder is coming down. It's falling down. So this should be a negative rate. And we divide both sides by 10. And we get dy over dt, I put it over here, equals a negative, say 12 feet per second. So as this is moving out of 5 feet per second, you're actually coming down at 12 feet per second. This is dropping much quicker. It's pretty scary. Have you ever been on a falling ladder? I have a couple of times. It's not a lot of fun. So that's the last time caused me back surgery. So that's how we do this. 12 feet per second, going very rapidly. Try to grab onto something. Okay, so there's a couple, 3 examples. I think I have one more here. I haven't actually tried this one, so I'm going to try it now. It says a spherical balloon is inflated with helium, so it must be a circle kind of like thing. And how fast is the balloon's radius increasing at the instance the radius is 5 feet? How fast is the radius increasing? When this reaches 5, what is dr over dt is what they're asking. The spherical film is filled with a rate of 100. So this must be the volume. That's the rate at which the volume is increasing. dV is over dt is increasing at 100 pi cubic feet per minute. I don't know. I haven't tried this one. I hope I can do it. So let's give it a shot. Formula for the volume of a sphere is volume equals 4/3 pi r cubed. Remember that. So dV over dt equals 4 pi times 3r squared over 3. So these 3's look like they'll cancel out. Well, we know dV over dt, it's increasing at 100 pi feet per second, or cubic feet per minute. And we know 4, we know pi, we don't know the radius. And when I did this, I should have put dr over dt, huh? We don't know the radius squared, do we? We'll put that down. But we know dr over dt. Oh no, that's what we're trying to find. We do know the radius. Excuse me. The radius is what? 5. So that's 5 squared. And we don't know dr over dt. That's what we're trying to find, the rate at which this is increasing. So it looks like we have a nice little equation here. We can multiply this out. This is 25 times 25 times 4. Let's see, that'd be 100, wouldn't it? 25 times 4. 100. So we have, let's just write it this way, 100 pi equals 100 pi. Kind of weird, huh? dr dt. And we divide both sides by 100 pi, we get 1. So this is the radius is increasing at 1 foot per minute. And I guess that's the answer to this. See, it didn't seem that hard, huh? If I did it right, and I think I did. So the radius is increasing at 1 foot per minute. If the helium is in the balloon, the volume is increasing at this rate. We don't actually know the volume, but we know the rate at which it's increasing. So dV over dt, these indicate rates, instantaneous rates. So we found out that the first derivative could be the slope. It also can be the instantaneous rate in which something's happened. So I hope you enjoyed this little video, and it should help you a little bit on the quiz. Where are we? Trying to find this little thing.